Good evening, everyone. So, I welcome you all to the day 8 of the training in the FPGA development. Since day 7 and since today, since the day 1, we have created different methodologies. We have followed different development flows to develop an architecture or some kind of application on FPGA. So, as of now, we have seen different types of applications on FPGA. We can use a memory block, or we can use an AND gate or OR gate, very simple. And also we can use processor. So today we are going to develop the processor on the FPGA architecture. So now this processor has different components and different elements in the architecture. We will go through each one of them. And today's agenda is to develop a soft core processor called Microblaze on the FPGA development. Same as we have done yesterday, it's like getting the IP blocks from the different vendors. And imagine you are doing an industrial level project now, and in the real time, it will be very similar to use the IP blocks and generate the VHDL and writing the test benches, verifying them, and these are all can be done in a single simulation flow. And you may not be worrying about writing test benches because that can be done by another verification engineers, and your intention is to synthesize the RTL design and also implement the design, then push forward this project of yours of the implemented design, successfully implemented design, to the verification team where they go through the simulations and verification through using test benches. So I welcome you all for the day training. Thank you for being here every day, and please be consistent in daily classes. Look into the subject and make notes. That is the reason I am holding this content on the YouTube for everyone's access. Some of you are in the semester exams, and some of you might have some personal troubles, and some of you are also having some network issues to attend the classes, and so that you might miss some of the live sessions. It will be a it will be an issue, but you can have this YouTube video within the 24 hours window. The access will be given to everyone who have enrolled to this uh, training, and it is completely free on YouTube. Please do watch before the 24 hours window completes. And if you need any other further access, right, just please let us know. We will be trying to give the additional access as well to extend the time limit, because some of you are genuinely trying and very serious to learn this skill. I really appreciate each one of you, and I hope you will be becoming the best engineers in the industry. That's what our aim is, to transform your student career to a professional industrial engineer career. So that is our agenda. So let us go to the today's agenda. So today's to do, as I told, creating a processor on FPGA in the Vivado. So this is the major task. Yesterday we have implemented only block RAM memory. That's a single part. Let us take in every processor or in every chip, we should have a memory block or memory registers. So those are there for at least a catchy instruction registers, like they push forward the memory for few set of milliseconds or nanoseconds, and then there's those memory blocks are used only for the operations and any arithmetic or logic operations. So likewise, today we are building a complete processor. So we are giving the FPGA chip the processor application, and that processor we can design in softcore version or hardcore version. There is a little difference between softcore and hardcore. When I say softcore, right, it can be configurable. It will be very easy to configure at any point of your design. It is easy to add peripherals and manage the peripheral operations, and also it can take security interfaces and whatnot. You can do all the sandbox tools or things that you want to develop on the software processor. But hardcore processor, It is designed for a specific application. Again, it is not an ASIC design, but hardcore processor are very limited versions of designs in developments. So you will not be having any feasibility or free hand on developing any applications on hardcore. It has certain restrictions depending on the design that you make. So based on the this thing today, where we are going to the processor, right? We will be introducing to the architecture of it and how to design processor on the FPGA. So today is our project 4, and what is the project for today? It is of microblaze processor development on the FPGA. So generating microblaze processor with tickle commands in Vivado, that we will also see as I have introduced tickle. It is a set of commands language that we use for development of FPGA architecture. So understanding VHDL by example. So we will try to do all these things because today VHDL will be created by the EDA tool. We won't be creating anything. So as it was done yesterday, we took an IP block and we created HDL wrapper, and that HDL wrapper gives all the VHDL codes that are required for the internal components. So today let us go to the practical experience and get ready with your Vivado tools, guys. Here you can pause and open the Vivado tool and start doing right away with the following of my slides. Come along and let us go to the next thing. Let us introduce ourselves with the microblaze softcore processor. It is a 32-bit processor and it has a reduced instruction set core processor, like RISC that we call in the industry. RISC architecture is mostly used in the embedded applications like IoT, and also in the automotive industry. RISC-V processor, RISC-V version is prevailing now, and it is very good skill to understand RISC-V architecture, and you can research on it. You can research some articles and you can enroll for another additional trainings on RISC-V. If you have RISC-V architecture understanding and working experience in your career, in your resume, it will be an add-on benefit. So uh, keep a note of it, guys. You can work on RISC-V. If you can ask me, I can direct you some sources. I can give you some sources or some additional trainings where you can find the authentic ones. And so it is programmable. For example, if today's agenda is like developing a processor application on the FPGA. So now your FPGA is a softcore processor now. You have turned your FPGA chip, which is unknown, which is not developed in the earlier stage. And now take this FPGA, embed this microblaze softcore processor on it. You are writing something on it. You are making architecture on it. Okay, now FPGA processor has microblaze softcore processor architecture. So this FPGA is microblaze, and on this softcore processor, you can run some microcontroller projects. Very basic, like you can start from C programming, implementing Arduino. And some of you might have asked me how to implement artificial intelligence on the FPGA. It is like developing a processor, developing the required hardware. So now FPGA is a tool. Let us say FPGA is an environment. That environment has different set of elements in it. Like you can build a 32-bit processor or 64-bit processor based on it. The RAM you can build as a based on it, and you can build 2-core, 4-core, octa-core. You can build how many cores you need. So you need to define the specific hardware on the FPGA. Based on that hardware architecture, you can implement the size of machine learning code. You can start from basic machine learning code and to the wide range of machine learning codes. For example, basic application of AI is object detection. That's a project on my Python that can be done on microcontrollers, and you need some hardware like camera module embedded for the Raspberry Pi or Arduino or ESP32. And if you have that kind of hardware and if you give the enough power source And if the processor, if the node MCU processor, if in ESP32 you can see node MCU processor. Likewise, in our Mars AX3 board, FPGA board, you are embedding microBlaze. Understand, guys? If you go for ESP32 microcontroller, search for it, you will see node MCU architecture. And in the same way, MCU is nothing but microcontroller unit. So node MCU, that was developed by some company, some vendors who develops ESP32. In the same way, now you have Mars AX3. You have everything in it. You can build 32-bit or 64-bit. But this ESP32 is like, it's a 32-pin microcontroller, and it has some certain cores that are built. It's like a hardcore. Now you have sandbox with you, and you want to build some application like artificial intelligence on it. Define the hardware first, write down specification. So how many cores you need? You don't need to you shouldn't be burning the FPGA chip. So we should have higher specifications on the FPGA board. So go for RAM, how much RAM you need, and how much memory you want to process, and how much SD card that can be accessible. So it's a major process and major project. It's different way, but I can guide you in this way that you need to develop some processor architecture on FPGA. After you develop something, you can run whatever code you want to run on the FPGA. So you need to integrate some of the libraries. So it's a vague area that you go there, but it will be a good effort if you try on that. And some of you have asked. I really appreciate that enthusiasm, and I think they were creating something in their final project, final year project. I hope, guys, you will be doing that. In this training, we won't be going there for any other thing. This is like beginner to advanced level, introducing all the elements on developing the FPGA. It gives you a good idea on how to work in the industry and also develop your own ideas. One of that own idea is like artificial intelligence. You can apply on this FPGA processor. If you can apply on any microcontroller or microprocessor, you can apply on the FPGA by developing a processor architecture on the FPGA. So keep in mind now, as we are developing the processor, software processor on the FPGA, we are writing hello world. In the same way, if you develop processor on the FPGA, so then you can also run some other language code, and you can get the peripherals attached to the FPGA board, and from there you can collect the data through the sensors or through the peripherals you attach for your ML project. So it's such a simple task, and yeah, that's it. So going further, microBlaze processor can run parallel in C and FPGA resources. For example, you have written some hundreds and thousands of lines of code in C program. What it does is very basic application. Like some of the instruction sets or some of the execution loops can be done using C libraries, and some other processing or some other functions in the C program that you have written can extract the help of architecture on FPGA resources, and that FPGA registers can also help in executing the functions of the C program, such that the process of executing the entire C programming file will be very fast and very easy to process on the FPGA process. So that is the reason they run in parallel. So they will use some of the abilities of C program file and some of the FPGA resources file. So it is a hand in hand application on the FPGA architecture. That's a best application on FPGA. So keep in mind, these are the eligibilities of FPGA architecture. You should remember all the time that okay, our FPGA is very powerful chip that we are designing now. We are designing the chip in terms of hardware, in terms of utilizing the hardware inside the chip. So as I told, I am reminding you all, guys, we have two types of chip designs. One is FPGA design, field programmable gate array designs. One is ASIC, application specific integrated circuit designs. Like one thing in FPGA, those are manufactured with lacks of logic cells and also predefined connections and pre-designed connections. They are not connected, but you have wires, nets, cells, ports, pads, inputs, outputs, all you have in this FPGA architecture, but it is unknown application. Now what you are doing as a user or as an engineer, you are taking this FPGA chip and writing some architecture to it. Architecture is nothing but, okay, some set of cells should do a memory application, or some set of cells should take the interface of video graphics, and some set of cells, logic cells, should work as a counter, arithmetic logic operation, or any other calculator. Your FPGA chip, you can design it as a complete calculator. Yeah, you can do it. So you can attach your USB keyboard and you can do some calculations. So that is very simple. So it is manufactured with some set of hardware logic cells inside it, and now you are attaching architecture. In the ASIC, in the application specific integrated circuit chip design, you are designing the chip according to the specifications and according to the application of the industry. So you're setting the industry standards and specifications first. Like some vendors, take it as a Samsung as an example, or Nokia as an example. Nokia is a well-known company. I usually refer Nokia many times because they have done the real implementations of the chips from basic to advanced in the mobile industry. You all know it ruled mobile industry in the beginning. So take a Nokia company. Now they are wanting a chip for the next 2-3 years to develop a phone, mobile, and they want all the applications at once, like camera, display, Ethernet module, like for 5G signals, and also for Wi-Fi module, another processor chip. And also it should have power optimization, like battery optimization functionality in it, and it should run software on it, like OS, Android OS on it, if they have own OS on it. So it should utilize all the registers or the logic cells or any other thing in the beginning itself. It should be designed in such a way, Nokia chip that it is using. So for that OS application, for that mobile application, we are designing a chip based on it. And this chip cannot be used for any microcontroller project, or it cannot be used for any IoT project. Okay, you can have IoT application from Play Store, and you can link your hardware, IoT hardware, to the app through the external server. That is a different scenario. But what I am asking is, now we are developing FPGA architecture with some processor on it, processor application. Now this chip can be used for Internet of Things, or this chip can be used for electronically controlled units in the automotive industry, ECUs. So this has wide range of variations. That's the reason we can reset this architecture and we can rewrite it all the times. So it's a field programmable gate array. Hence, so in the ASIC, no, if you design a chip for mobile, it's for mobile. If you design a chip for laptop, it's for laptops. And if you design chip for personal computers, it's for personal computers. And if you design chip for some PLC application or for some communications application, it is done. It is for specific application. So application specific integrated circuits, IC. So both chips, don't get confused, guys. Here you have softcore, hardcore. Here also you will have some soft macro design or hard macro designs, completely unique. So let us go. Alternative to the microblaze. Okay, now why do I explain all these points like alternative, Jink processor? Why do I want to confuse you? No, it is not a confusion, guys. As I told earlier, the best tip to become a well-known or well experienced engineer is, you can note it down. I have repeated it. So tip is, you need to question what, why, how, and where it is applied, or where it is coming from, or who has done it, and You can ask these WH questions around a topic in your learning experience, such that you will be way ahead of your regular colleagues, and you can also understand a concept in different ways. If you can't find answer in one certain point, search for the answers in different domains. So world is open for you, and your generation, it is very advantageous that you have internet access across the globe. So use it wisely for good purposes, and then you can see the answers and results according to your question. Definitely there will be an answer. If you arise a question, there will be an answer. So without answer, you can't get any question, but you will achieve there with a good knowledge, with good experience on it. So I should say alternative, because some might also think there will be only microblaze processor. No, it has many other versions. I mean, not versions, competitors. We have Samsung and Apple. We have Nokia and Panasonic at the earlier stages. So everything has an alternative. We have Xilinx now, and we have Intel Cortex Prime. Cortex Prime is another EDA tool like Xilinx Vivado. I mean AMD Xilinx Vivado, Intel Cortex Prime. So Altera Cortex Prime. So both are two different things I have explained in the beginning classes. So let us go to there, and we can create simple Hello World project. It's an application. Hello World is an application, so it should display Hello World. If you attach LCD display to the FPGA board, if you interface it, you will see Hello World on the FPGA. How do you see that Hello World? This is the class today. So let us go to the understanding of architecture. You should understand, at least you need to understand the basics of it. How these internal components will be dedicated to the working of the processor. So it is again the microblaze soft processor architecture. It is a complete architecture. This is how we define a processor. Processor should accomplish set of tasks parallelly at once, without any time delay. That is our goal. So when you say processor and when you say controller does only one task at a time, but processor can do set of tasks. You all guys know. Don't get confused. So now we are building processor with set of applications. If you click button, it should blink LED, and it should also display on the LCD. So it should do both the tasks in the same way. I have given some basic example. So understand what are the components. So today I have introduced architecture directly to you. If it is the first class to you, just understand elements of architecture. Do we have same elements for every architecture? Might be. Some basic elements are, take it as ALU, program counter, instruction decoder, and memory management unit. Basic. And data side bus interface, instruction side bus interface, instructions, data bus interface, and you can see bus interface, and ALU, shift registers. ALU is a register, shift registers, barrel register, multiplier, divider, FPU, and ITLB, UTLB, DTLB. All these internal blocks, don't get confused. So these are determined by the architecture made by the vendor. The microblaze was made by some vendor, and you can understand these internal blocks by going to the data sheet of that. But let us understand the external, like outer line. So we can see memory management unit, and it has some internal blocks, and we can see some ALU logic blocks, and you can see internal projects and special purpose registers, uh, and also instruction decode, branch target cache, instruction buffer. So basic elements: instruction decoder, program counter, bus interface, database interface, and arithmetic logic, and register file 32 registers. So you can see input and output and processing. As I repeat every time, whenever you see some application or task or some functionality or some code, you need to check for what is the input and what is the output, what we need to do in between the input and output, like it is the process, such that we will get the desired output. So as a programmer or as a designer, you are looking for 32-bit registers or 32-bit interface FPGA processor. Your output should be 32-bit, and you should give 32-bit, or you can give any types of inputs, like you can give 2 input, 4 input, 16 input, and if you give 16 input to two multipliers, they will multiply it and they will produce another 16 things, and you can give it to, you can increase the size of bit and you can get the 32 again, but you are getting 16 into 32. So data is divided and packets are divided into 32 with some dummy message inside the packet, so it is different scenario. But you should think about input, process, and output. Depending on the output, desired output, you can design the process inside it. It's nothing but input, and you can see the output on this thing. These are, don't worry about this nomenclature. Nomenclature varies between every architecture. This is the architecture of microblaze softcore processor, and you can also look into the basic architecture of ARM processors. ARM processor architectures are the real world applications in this chip design industry. Whether you take FPGA or ASIC application chip, you can take ARM as the best example. If you understand ARM architecture, your recruitment or your hiring chances are very high. So, as I told, RISC-V architecture is one thing. If you understand and have hands-on experience on RISC-V, very good. And if you go for ARM architecture understanding and working and development of ARM architecture, your chances of getting recruited is very high. And don't worry about developing and working on hands-on on ARM architecture. Understand the architecture first and try to develop it in the assembly language program. If you can write assembly language and if you can understand it, you can also write C programming, building the ARM architecture, everything. You need to go around this ARM architecture to get well knowledge. So ARM Cortex M0, you can take the architecture, read about the data sheet of the architecture. You will get the user manual online. Then you can go through each instruction sets. What is this instruction set called? Now we do have microblaze softcore processor architecture PDF. If someone needs this architecture PDF, you can ask us. We will be providing you. So okay, without any delay, let us go to today's creation of microblaze softcore processor on the FPGA development. So this will be your practical experience on developing the processor architecture on the FPGA. So do along with me, as you have understood the architecture and applications of softcore processor. You are pretty sure about processor now, and now we are developing processor. So see guys, every day we are learning some new things in an evolution way. At first, we have developed only one logic cell, that is AND gate or OR gate application in the entire FPGA. Now what we are doing? We are doing some processor architecture. In between we have done IP integration, some of the memory blocks. But today we are developing with group of blocks into a processor. Yesterday we have done with one block. Today we are doing with group of blocks with the help of IPs again. IP integrations. It is an automation guys. I'll explain in the flow. Open the VHDL tool, create a new project, click on next after seeing this window. You need to name your project name. It's my project location is Vivek. Don't get confused. I am Venkat Kamal, so it's my shortcut name for my PC. So project underscore microblaze. I have named it in this way. You can name it anyway. You have that feasibility guys. Don't get restricted to what I do. You should do exactly the same. It is helpful if you do the same way. There are no restrictions. So declare the RTL project type, and you should also mention do not specify sources at this time. See, Earlier, if we do not check this box, it will produce some VHDL on its own. But today, we are taking group of IP blocks. We are automatically connecting them. EDA tool does that for us, and then we generate VHDL. So click on next after you select the RTL project. As I have been explaining every day, you can see it's an IP integrator. It has RTL project type. You should mention RTL project type. And if you are asked why you are choosing RTL project type, you can answer that it has generated, we can generate IPs, we can use IPs, and it can be RTL analysis, and we can run the design flow of FPGA development from analysis, synthesis, implementation, and simulation. So you can do all these things. Click on next, select the board as it is. We are selecting the packages like uh, PSG 324 and speed grade 1. It shows you some family, subfamily, and you are selecting the same board, Mars AX3 board. Please make a note of it. And later you can go for this project summary, finish it, then come to the Vivado EDA main window. You can look into this, and then uh, what you can see, this is the project manager. You understood the flow navigator, right? Project manager, IP integrator, simulation, RTL analysis, synthesis, implement. This is a flow. Don't get confused. We are doing the same thing throughout all these days. So today, if you follow along, it will not be a new thing. Learn it as a fresh application or fresh development flow. You will understand. First, we need to add a project manager, all these things. If you add files, if you add file location, so your project will be in the good file location. After you have the file location and folder, not only this project, every project you develop, whether you became an embedded C programmer or any other hardware or embedded software project developer, you need to work on the file sources first. You need to set the locations of the project. In that project location, you need to work. So there is no confusion in it. Go to the add sources as we have done earlier, but come to the IP integrator. Okay. Now, okay, I'll show it here. Come to the IP integrator. Today, we are not adding any sources. Earlier in OR gate and AND gate developments, we have took sources. I mean, we have created VHDL, we have created test bench VHDL. But today, we are going through block design development. So, creating a block design, very good. Take the block design in the next window. We can see, click on the block design in the left using IP integrator. Click on create block, and then go to let me take a pointer and explain you well, so you can understand. It's a IP integrated usage. Today we are developing uh, in the flow of taking group of blocks or taking the processor microblaze IP integrator. Why I am using IP integrator? This intellectual property called microblaze processor is already developed by some vendors in the industry, and now we are taking it and we are specifying our own specifications on the IP, and by the own specifications we are generating the VHDL out of it, so that VHDL we are using to convert it into bit streams, and we can use it for simulation purposes as well. And when you generate bit streams out of VHDL, right, you can upload it to the hardware, you can export to the hardware, and when you export the hardware specification file, which is ready to be flashed on the target hardware board, physical board, so then that file, hardware file, after your generated bit stream, it can be used for external IDE, integrated development environment. So by that IDE, if you that IDE develops C programming, so to develop C programming, it should need what is the hardware required. So it takes the hardware mapping to this hardware file that you export after doing this project design. So we'll go through a flow. Now first step is taking the IPs by creating block design. Now go to this window. Now, after clicking on block design, it will appear. This create block design will appear. Name it as Emblaze, and you don't need to change this and this. And click on OK, and you can go to the this window. This window will appear when you click on that thing, and when you show this right click on it, and when you right click on it, you will see this pop up, and you can say add IP. Do you need to add IP? Yes, we need to select IP as we have done in the yesterday's block RAM IP integration. Please do check out that lecture and come back to this. It will be a better understanding of thorough designs. It's the same flow, taking the IPs and developing the architecture on the FPGA, whether it might be a single memory block or whether it might be a complete processor. So, and you can select microblaze by clicking on it. Select this thing. You don't need debug module or MCS. You This is the window which it shows the list of IPs that are available in the EDA tool. So in the EDA, we already have some licensed intellectual properties that we can use, and we can create a design on our own. Like I said, we can take processor, we can add other IPs like display module, Ethernet module, and other counter module. Any other thing we can attach as an IP, and we can create our own design. It's like cooking, making our own things. So go to the microplace, and then this window will be seen by you. Do it along. When you see this window, you can click on run block automation. When you click on run block automation, what is that run block automation? Whatever components required to make this microblaze processor work, all these components will be getting dumped into this IP. We don't need to select individually. This is all block automation. This is a required skill as well. Nowadays, automation is the key. When you understand the automation, when it is made simple, it will be very easy to debug and rectify the errors in the real time. And if you sit on design, only the design, it might consume your efficient time, but mostly we should be working on errors, and we should come back to the design again. We need to modify and go to the simulation. If we have errors again you need to come back to the design, analyze, simulate, correct the errors, and go to the simulation. And if you have no errors, push forward this design to the manufacturing. That's what happens in the industry. So you design, analyze, simulate, and you get errors. Come back to the first flow until you get a clear design. You are not pushing this to the next flow or the next team for manufacturing. So I'll try to explain it in a flow diagram in later stages how you will be working in the industry. Understand the outer line. I have repeated twice. I'll repeat it again. So after you click on run block automation, right? I have just highlighted this. Click on block automation. This is the next step, and you can see some specifications, configurations. You need to select all these check marks here, and when you click on it, you can see you need to mention local memory and ECC. Nothing to be mentioned. Cache configuration 16 KB. Why are we giving this architecture? So every processor should have a specification. What are the specifications of i7? I7, it has a 7th generation or 4th generation. In the 4th generation, it used to have 2.2 gigahertz clock, and it used to have 12 GB RAM. And in the processor, it can be having 8 core. It used to have 8 core, and it is as near to the mobile chips as well, but it is powerful, that i7 architecture. So in the same way, we are having cache configuration, local memory. Whatever local memory you have, you can increase or decrease the cache memory, but it is ideal to keep bare minimum of the local memory. If you have lesser cache is nothing but uh, I think it as imagine it as a place where before you get your data processed, it should wait in the some location in the registers. That location you can name it as cache, and it's mostly used in the faster calculations because you can redirect the data path to the cache and this cache memory and use this cache memory to the processor processing of any operation or application on it. So sometimes cache memories are very vital and plays crucial role in the processing in the design. So next, debug modules, debug and URT. You need to add URT module again. It's an IP again. UART is like how do you interface using microblaze processor with the external peripherals. It's a UART is like an interface. It's a protocol. Understand? So and peripheral AXI port. AXI port, so like it's a translation protocols. So we usually call it as an AMBA protocols, AXI, AXB, all these things. Mm, I will try to explain those protocols in the before completion of the training. We can explain them with the best examples of Verilog HTL development as well. Next version of this training will be on Verilog HTL development, complete Verilog HTL development using some uh, electronic design automation environment online. You can have online simulators and then you can work on. I'll show you how to work on. There is no limitation of hardware in the learning of Verilog HTL. If you learn Verilog HTL, it's a powerful tool, and if you understand EDA Vivado, it's another powerful thing. And if you understood the architecture of processors and FPGA board, and if you have this all sessions experience, wonderful to know. So your profile will be shining enough. And what are the external skills that you should acquire before the completion of final semester or before the completion of the market recruitment? I'll be listing out in the later classes. So as of now, clock connection, you can keep it as 100 megahertz. It will be showing, and click on OK. Then you can go to this automated generated connections with the architecture, and you can see the major part is like this is the microblaze processor, and it has all the interrupts, debug, and uh, these are the output ports again. So clock and reset. So this clock and reset, you have clock wizard, you have microblaze debug module, and debug module is the basic one. Microblaze is the processor here, and it's an entire processor, and it's like a control unit. And with the control unit, if you have all these set of elements attached to it, it is a processor now. So then again you have processor system reset. System reset is another thing. If you enable it, if you click on some button attached to this system reset, na, entire architecture functionality or the programming language you have written on it, like C program, assembly level program, or any other object oriented programming languages that you have written on it, it will all be reset, and you can rewrite the program again, and you can rewrite the architecture as well. So system reset. And you have AXI interconnect. This is mostly used for the external peripheral interconnects. And now you have local memory. As I told, every processor should have local memory, clock, and debug module, and also reset, system reset things. And you will have output peripheral connections through the some protocol. So you understood. We will add UART. UART is not seen here. UART will be added in the process. So understand, you have created IP using IP Integrator. Click on IP Integrator. You can see this. Run block automation. You can see run after running block automation, it will be asked for specific for configuration. And if you have seen that configuration, according to that configuration, you can see the nets connected. How are these nets connected? These are the nets connected. So and then now you need to select the clock wizard. Click on the clock wizard. If you can double click on it, you can see it is highlighted here. And if you click on double click, you will see the customizing clock wizard. So what is the importance of clock? As I told, in any processor or in any digital circuit, clock is like a heart or pumping system, and it is the required element in terms of transmission of the data according to the synchronized clock pulses. Clock pulses, we have named it, we have termed it after the digital design, but earlier it is just a block where uh, it is used as a reference element in the terms of clock generation. So in this clock wizard, we have set what is the clock frequency and what is the operation of clock. You can see clock frequency should be set under 50 megahertz as a basic design, and in the nanoseconds you can convert the frequency into nanoseconds as 1 by 50 megahertz. Then you will get the clock period as well. So that is how in the industry we calculate clock period. So if we know frequency, we know the clock period as well. So why it is required? The data transmission of the packets 1010 and this bit stream, whether they should go in a particular flow, they should have reference according to the clock pulses. For example, for those 5 clock pulses, you have set some 8-bit data, 1001 and 1100. If this is the 8-bit data, it should go with the 4 clock pulses, let us say, and for every 4 clock pulses of that instance should carry this packet all the time. So it's a reference element. If you miss one bit out of that 8 bits, right, the data will be lost. You will get another error. So there shouldn't be any slipping of clock pulse according to slipping of clock pulse, like introduction of the delay due to some other external elements in the processor. So don't get confused too much. I'm just giving a virtual example. So that is the importance of clock. Based on the clock, these entire sequential circuits will be working on. And major difference between combinational circuit and sequential circuit is the clock. So after you set up this clocking options in the primary 50 megahertz, scroll down, and you need to select this single sounding thing. Mm, these are the two things you need to mention. You don't need dual tone clock thing. You need only single tone. And check out for this as well, it is important. And in the next window, click on output clocks and you can set it as active low at first, like it starts from 0 and it goes for 1 again. So you will be seeing this block with one clock, single clock, as you may have mentioned, one single source, and click on next. Then after clicking on next, if you have changed any other element in here, right, every time you need to run connection automation, because based on that connection automation, these will be internally connected. So once we are very sure about our architecture and design with the connections, then we will be so sure to work on. So before running connection automation, when you click on connection automation, right, it will appear this window. You need to select all these elements and click on OK. When you click on OK, you can see this. These are the new connections attached. Don't worry, I will show it in the next big window. Now you can see this connections. So now this reset is left alone. We don't want two resets. If these are left alone, this architecture will understand, okay, now this has two resets. Why do we need two resets? That's an utter flop, utter error. It will obviously show an error, and one is a free floating wire. You shouldn't have any floating wires. And then one reset, we need to connect it in the next window. Place your cursor on this reset pin you can see a pencil wire, and that will be connected in the reset. If you draw a line to this, you can connect as it is. So as you can see, if you can draw in this way, if you place your pen cursor on it in the window, it will, you can direct it in this way so that it will be connected automatically. Then after connecting, you can see, you can change the names as per the reset n. So click on that reset port and change the reset n port. Same way, you can change from reset RTL to reset n, and clock underscore RTL to clock underscore 50. Just click on the ports. You can see the neighboring window. There you can change. That's it. If you can change, and then in the IP window, right? You can click on, right click on it in the diagram window and add an IP called UART light. So as I told earlier, we are adding UART now for external interface. So add UART and click run automation again. Yeah, run connect automation. You have changed all these things, right? This clock 50 and all these things. You need to run automation. Guys, again, I am telling you, you may write reset underscore n, or you can also mention it RST underscore n. There is no hard and fast rule to write it in the same way that I have written. You can mention it in the own style of yours, but in the designs, it will be very good if you elaborate the names. Another tip while you are writing, and remember these names after you write in the VHDL codes and test bench codes as well, because you will be making constraints out of it. When you make constraints, you need to be very specific at the port names. So I'll show you in the a bit later version of class. Now, when you click on connect automation, yeah, you can see these are the wires that are not connected. You can click on these connections and click OK. It will automatically get connected in this way. So all these pins are utilized. So you can see architecture is uh, well connected now. So now you can see, and after this automation, after this connection, right, you can go to the regenerate layout. Nothing but you can see a flow of architecture. You can specify these connections. These are randomly spread all over the place, and there is no particular for what comes after what module. So every element will be aligned in a particular layout. So if you go to this icon, you can see regenerate layout. Remember these things. These are the shortcuts, and you need to be very familiar with the shortcuts such that you can see a clean design now. What is the clean design? These are the clean designs. So clock wizard, after the reset, processor system reset, debug module, it checks the errors. If you want to check the errors and if you want to test the processor, debug module is must. This is the processor. As of now, don't worry about input output ports. Those are all designed by the IP integrators. Don't think too much out of it. Understand it is a set of blocks come together, attached and connected together to build a processor. So AXI interconnect, it comes here, and microblaze local memory. Now you can see this entire interconnect will be responsible for peripherals. That is the reason at the output you can see AXI peripheral and UART light. These will be communicated. Hence, a transmission of data, basic example, understand in a virtual way. Imagine it, you have a data here and you need to display it. You have some binary input, binary output from the processor. Let us say 1010 or 1001. If you have binary output 1001, that is transferred to this AXI peripheral connections, and it will look for some hardware, whether you have LCD display or LED displays, or if you have group of LEDs connected in a sequence to display digital numbers. You have seen boards, right? In railway stations, you can see boards which are having LED lights, and in that LEDs, the data will be transmitted in a sequence. Such hence, the data will be in a scrolling manner. Human readable interface. You can see the alpha numeric nomenclature on the boards of railway stations. There they have processors. The binary output will be given to the AXI or some AMBA protocols, AXB, any other protocol if you know. Understand these protocols through some external sources. We have different materials out there, very much essential skill. And these protocols, they will make all these data to be processed, I mean data to be transferred and converted into our own uh, human readable thing. It is transferred to UART protocol. After the set of protocol instructions in the UART peripheral, in the UART element, it will be going to the output, whatever is connected to this UART light. Whether you can choose LEDs and you can choose LCD display as well. So LCD display, I'll show it in the end of this code. So now everything is connected, and then after regeneration of the layout, validate the design. How you can validate? Click on F6 or you can click this button to validate the design. Why do we need to validate? We need to check the design with errors. They say critical warnings, but warnings are negligible but to be taken care. Every time you have two types of difficulties after your design. Yes, every engineer gets stuck at this point. You should go through errors, you should go through warnings. So it is what it is. I mean, it's an engineering task. Not only designing, error rectification is also an essential skill. So that's what we are learning now. So go to this validation. If validation is successful, generate HDL sources. Very simple thing. Now you have block diagram. Where is it? This is the dot bd file, block design file, whatever block design like emblaze block design. So I think in the earlier pages you can see somewhere it should say microblaze dot bd. Yeah, this is the microblaze dot bd. I can show it in the okay. I can show it in the window. You can see this is the architect. And here in the sources, yes. See guys, okay, I can't zoom in more. Microblaze.bd. If you right click on it, create HDL sources. I have already created. You need to create now. On where you need to create .vhd, that .bd, you will see only bd file. And if you right click on it, and if you create HDL wrapper is nothing but for all the components, the HDL file will be generated. How do you want to change that HDL source in the project settings? If I say Verilog, you can change VHDL to Verilog. I mean, I don't want to change now. I got to stick on VHD. If we work on VHDL right now, and we will be going to Verilog HDL, such that you will be having both the experiences. You will not be frightened. See, many of you will be going to a fear state when you see some new things. Don't get feared, guys. Face the challenges. It is like coming out of the comfort zone. So it is must required skill. You shouldn't be in a comfort zone. and you will be in comfort zone when you achieve your all essential things in your life. So until then, work hard. So make a habit of getting introduced to the challenges. Face the challenges bravely. You can face. It's like a uh, instant thing. If you decide, you can do it. So usually, what I do is it's like 5 minute rule. I mean 5 second rule. 5 second rule is like whenever you want to do something, right? Check on yourself like, okay, I want to do something, but something is stopping me. You don't know what it is. There might be some procrastination, there might be some laziness. Let us accept our humankind, human things, and there might be some obstacle. But every time to accomplish some task, if you say this one powerful tool or tip that I am giving you, it's a 5 second rule. Count from 5. It's like 5, 4, 3, 2, 1. Done. Now I will be doing this. If you make up this kind of mind, you will accomplish everything. So, a part of this, let us go to our design. You can see after this validation, and you can click on automation, and you can also check validation. It is successful. Now we are creating HDL sources. First step, create an IP block, and second step, run block automation by adding the elements. Third step, connecting them, like run connect automation. In the fourth step, we are adding UART light interface and also change the names of ports reset and clock port to clock 50, clock underscore 50, and reset underscore n. And we also connected reset pins from the clock wizard to the reset pins of the entire power system resource reset, power system reset module. So entire architecture should have one reset. Entire architecture should work in one clock. Okay, you might have different clocks in the different set of applications, but as of now, for our processor basic application, we should have one reset and one clock. That's it. As based on that clock, entire design works. So HDL wrapper, create HDL. You can see. Uh, let Vivado manage wrapper and auto update. Okay, it's like we are not writing complex HDL codes. I will show you the HDL codes as well. In the yesterday block RAM design, we have designed only one IP block. We have used only one block so that it will be easy to take the VHDL and understand it. And if we need to change, we can change immediately. But we have bunch of IPs. It's a different task. Difficult to understand the complexity. If you make one mistake, we need to understand eradicating all the errors. Okay, we will be familiar one day. We will be familiar, right? Like we will be writing VHDL codes on our own for every block that we attach. We will be connecting on our own. Why do we need that? Every time we need to depend on manual as a plan B. Earlier, it is the only plan that is available. You need to design manually. But now, while you are using automation, best tip as an engineer is understand how to make it manual. If you don't have Wi-Fi, do you stop working? No. Do you stop learning? You should have physical handbook, physical textbook in your hands so that you will complete the work. If you don't have power, do you stop reading or stop preparing for your exams without any laptop? No. You will have textbook in your hand. You can make notes out of it and you can go for the exam. Depend on the manual things that are available, existing ones. You should have a plan B for every other task. So, uh, for a basic thing, go to let Vivado manage wrapper and auto update. It will auto update, but you need to understand how to change VHDL codes and eliminate all the errors in the later stages. You will eventually go there when you understand Verilog HDL as well. So, okay, now this is the VHDL it generated. If you click on this plus icon, you can see bunch of these sources. How did it prepare these VHDLs in a click of a second? It's very easy, guys. That is automation. Those are already there in the IP integrator. Those are bought by the uh, EDA tool to us based on our connections, based on our configurations on Clock Wizard, based on the architecture we design with the um, every other thing. So architecture on the controller, system reset or debug module, any other thing. So you can see all these AXA peripheral that has one VHDL. All these VHDL of individual blocks are attached as a single larger file. So that is what we call it as wrapper. So now go to this synthesis part and run synthesis. VHDL files are created, right? We can go for the synthesis part. Run synthesis. And when you click on run synthesis, it will ask to verify that top level design is emblaze. You need to check whether it is the emblaze itself. Yes, emblaze. You have created the diagram with emblaze. When you have clicked on IP integrator, you can see emblaze you have given. Save. Block design is saved. On that design, generated VH and the generated VHDLs, you will check the synthesis. So after synthesis, you need to add constraints. So add sources for constraints as we usually do after successful completion of the synthesis. Click on add sources in the project manager and select constraint sources as shown below. So this is the regular task, guys. I have written these steps to just recollect your memory, jog your memory in the earlier sessions. Usually we click on constraint. If you right click on it, if you click on add sources, you can see add or create constraints. Click next. And if you click next, so you click next, you can see this window appearing. And in the design window, so in the design layout here, you can drop down this. After you add constraint file, you can drop down this and you can check for IO planning. So like this. So you click on after synthesis, right? Go to the constraints, click on add sources, alt plus A, or else you can go for add sources for the project. So you can click on add sources directly. You can click on add or create constraints. So if you click on add or create constraints, you can click on add source. Like you can add files or you can create file. Once you create file, it is like emblaze uh, emblaze.xdc. Click on OK. Already I have. I don't want to confuse my project for it. If you want, if you any one of you want some constraint or any project architecture, right, I should be displaying it as it has a construction. If I disturb it, I need to start doing from the beginning. So not to make such a complexity, go to the constraints, and when you have constraints, go to the design plane. 1 second. Is it? And you can click on the emblaze in structure and layout. Okay, as it is done project, you can see this IP window as it is shown here. So in this IP window, you can see emblaze.xdc and device and package and the IO planning. If you click on the IO planning, right, you can see the IO ports. These are the ports for this processor, clock, reset, and UART input and UART output. So for this, you need to set up these package values P17, N15, U12, and V12. Remember these and keep it. How do I keep it? As I told, I will be going through the hardware data sheet. Our Mars AX3 data sheet has these values for the port declarations. We can use different set of ports P17 and N15 somewhere and U12 and V12. One is for output and one is for input. And the standard voltage is LV CMOS 3.3 if you drop down. So that is IO planning. Now After you click on control save, and if you ask for generate the constraint file, it will generate like this. Or you can write down this constraints file without doing this step. So in the beginning, if you click on add source, it will ask you to add emblaze.xtc file, and if you create it, you can add it directly by writing this code on it. And so set property, this is the command, these are the set of commands for xtc commands. These are the constraints based on the clock and input output ports. What is the signals that it should have, all these bit streams. So set the bit stream constraints of the design as shown. So these are the bit stream constraints. And clock, the period is 20 as I told. The frequency is 50 megahertz. If you do the calculation 1 by 50 megahertz, it is nothing but 20 nanoseconds. I hope 20 microseconds. Something period. You will be getting period in this way. 1 by 5 is 0.2. Hence, 20 is your clock period based on its units. So after synthesis is successfully completed, it will ask for run implementation. After synthesis, you can run implementation, but first open the synthesized design. Understand what has happened. For every step, take a pause, understand what are the design developments, go through the design developments and understand. That is how I explain and I work as well. So you can see some elements are highlighted, those are not highlighted, those are enabled. So that enabled design, till these many days we have never seen this highlighting thing. So as we can zoom in, 1 second, I will try to open this design in layout. So I need to run the synthesis implementation. Okay, for running implementation, I can open the design as well. It will take some time, guys. Meanwhile, I'll explain here itself. So when you see the connectivity, guys, some of the elements that are used, right? Group of elements can make you a debug module. Group of elements can make you a debug module, and group of blocks can make you an UART module, UART light module. Usually UART light will be sitting at the edge of the designs. I'll show once it has opened. And when you see this design, right, you can go to this design in the left side. In the scope, you can see these pins. And if you right click on it, highlight them with the color. You have done the same things in the yesterday's class as well, but today we are checking with the more number of processors. So logic cells, all these logic cells are used. If you zoom in, these are how the logic cells are connected inside. You will not be seeing the connected wires, but these are internally connected as well. If these are connected, you can utilize them. So likewise, all these blocks you can see, and now you can click on this all selected ports and you can highlight them into red. Let me open my design if it has implemented. No, it is under routing. So in the implementation, right, what it does is it takes the synthesized design. Before implementation, it will run the synthesis as well. After synthesis, it will take the design, it will place the cells. What do you understand by placing? Placing is nothing but placing is nothing but the nearest capable blocks that are available. If you are seeing microprocessor should be developed in the center, or a group of logic cells can be executed as a processor, and then all these are internally connected with the neighboring blocks, so that the clock, whatever clock you give, right, that will be transmitted very easily throughout the blocks. For example, let me annotate. So if this is your processor here, a group of cells, imagine guys, this is a microblast processor now. Hmm? And you have this debug module, you have this UART module, and you have this AXI interface peripheral module, and all these blocks are connected to microcontroller unit, that is this, and you have also clock. So it is connected here. If you place this clock, and it should connect to this, and through this it should go to this debug module, and it should go to this AXI, and it should also go to this user interface. You are late. Why do we need clock again? To accomplish the set of instructions, whether it might be data processing, data operations, or data transmission inside the microcontroller, a processor controller thing, and that needs to have a synchronized clock to uh, have the reference of the validated data transmission. So for that, and for enabling any device, you need a clock pulse as well to enable the use of this clock. And if you don't see any clock here, yes, some devices can be connected, some combinational logic cells can be connected directly to this, and they don't require any clock. But for every sequential cell, a sequential device that requires clock should be attached to the same clock for the entire design. So there is only one clock. So you can highlight. I hope my design implementation is successfully completed, and I'm trying to open the implemented designs. I hope it will open. Okay, it is taking time. Don't worry. So you can see the logic cells inside this. If you zoom in, open the window, click control, and if you scroll up little bit, you can see scroll down and scroll up, whatever it does. You can see the zoom, or you can use these parts as well. Zoom in and zoom out. So after that, the final step is to generate bit stream. You can generate bit stream. After your successful generation of bitstream, it will show a reports window. You can see each report. From these reports, if it is not matching the functionality that you desired of, you need to go back to the design synthesis. Before the synthesis, in the RTL analysis, you need to verify the RTL like VHDL codes, and then you need to change the specifications again according to it, and then you need to come back. You need to run the flow again. It is a complete iterations of flow. Remember, guys, you are not doing one time, you will be doing hundreds of times in the industry. So that automation, again, that type of simulation and automation will be done by the um, EDA tools. Hence, we require automation to us. So, uh, what other things you require? So you can see, you can check for the export here. If you open the file, right? I'll show you here. Yeah, this is the implemented design. Let me show you first. If you zoom in, you can see the bunch of blocks. Okay, so these blocks are internally connected in this way, and you can see it's a multiplexers, and you can see these are the lookup tables. Now lookup tables are inputs for these all logic cells. So what are lookup tables again? Those are the set of data inputs, like truth tables, like tables of information. When you set some instruction, right, all this data will be going to these lookup tables, and then lookup table will process it towards this logic cells. You can see using FPGA native LUT62 type LUT lookup tables. As I told in the OR gate implementation, right? OR gate is not the OR symbol that is living there. For OR gate, there needs to be some input. That input is lookup table. So lookup tables are much important. Those are pre-existing ones in the FPGA. Don't worry about lookup tables. All the lookup tables are having all the kinds of information. So if you can see in the output, see these are the outputs. So you can see test out. and you can see the reset, and you can see the power pins, clock pins, right enable. You have write back as well. There are set of registers in it. So these are the pins available. And if you can see some pads, IO pads, we are not using these things. Unbound means we are not using them. Go to the IO pads. We are using these IO pads as well. So yeah, that is it. This is the implemented design. You can go through the verification of it and come to this. Now let us check into the how to generate bit streams, right? So you need to go to the down below, and if you click generate bit streams, right, on this design to be fit here, you can see this. So after implementation, you can run through the generate bit stream. If you click generate bit stream, it will ask some set of questions. I think it is doing it right now. And after that, after generating bit stream, to run the C program, right, it is the last final step. So export your entire bit streams into export hardware. Now we are creating hardware file that is understandable by the hardware FPGA, that hardware board that we have. So export hardware, and this will create export hardware, and it will ask for include bitstream. Click on include bitstream. Guys, here we don't have hardware, target hardware to us, but we can see export hardware include bitstream in the local project. So hardware is not available, it will show this type of error. Don't worry, after you export hardware, launch SDK. If you have hardware in your hands, how to do it, that's what I'm explaining now. Launch SDK, it will launch SDK, view reports, open hardware manager, that's different. So now one SDK by the Xilinx. This is another IDEA tool which is supported by Eclipse now. Eclipse is another company which provides EDA tools. So that's the symbol SDK. It will open. So your bitstream has generated successfully. View reports or open hardware manager. Let us open hardware manager. There is no hardware that is connected. Now you can see the SDK file. Before that, you can see the wrapper attached to it, and this is an indication. Now when you open the SDK file, I'll show it will be shown here. The step is export hardware, export bitstream file, I mean export hardware, and also the next step is launch SDK. So after launching SDK, it will be shown like this. You will not be seeing any other thing. In the project explorer you can see. And now go to the file, create a new project. Now we are creating C program. This is not VHDL or any architecture development. Our architecture is developed, designed, done. If we have done implementation, it is done. So generating bit streams after implementation is the final step. Now, as I told earlier, we will be writing C programming on the architecture, on the FPGA to test it. How do we test it? It is in the same way. So open new, click on application project, and you have to mention the project name hello world, and you need to mention all these things. OS platform standalone, and hardware platform you need to mention emblaze wrapper HW platform. This is the file that was exported in the earlier stages. So when we export, right, emblaze HDL wrapper will be exported in the hardware. So hardware file, then select it, and select language C, create new. This is the BSP file. Click finish, and you click finish, you can see the hello world program created by the machine itself. To test it, write test on it, and if you have hardware, right, go to the run in the top, in the run. After you have written C program, you can write hello Vishram or hello your name. So then after writing your name, own name, don't change any other syntax. It is as it is. You can make it. It is the C program architecture. It's a syntax of C programming. I hope you all know. Then you need to go for run. When you run, click on run configurations. Set up the configurations as it is, guys. In this way, it will be better understood by the SDK tool to the architecture that we are developing. That is the hardware architecture that we have developed. We are making a synchronization. This configuration will be synchronized with the hardware we have, and click on run. So when you set up these things, right, set up the HDD IO connections as well, COM3, and target setup, and then click on run. When you click on run, actually it will run the simulation window in the down below here, and you can see hello world. And if you have attached hello world here, this LCD, if you have designed in the architecture, you can see the hello world here. So this is nearest to nice to see you in the same way architecture. So this is the LCD display that I am talking about. LCD 16 into 2. 16 into 2. 2 rows, 16 columns. So 16, 16 LEDs basically. So that's it, guys. This is the today's class. If you have any questions, right, just refer to the previous lectures, and also come back to us if you need any other additional support, whether you have academic challenges or if you have these lectures to get understood. Just talk to us. We'll sit with you and we'll try to make you understand. And thank you one and all. So yeah, Jai Hind.